Hello viewers, welcome to lesson 11 of module 4. As you know, module 4 is on payment design. This lesson will be about analysis of flexible payments. In the previous lessons of this module, we have discussed about general philosophy of payment design. We have considered various loads that come on payments in terms of traffic loading. We also discussed about climatic and other parameters that need to be considered for design of payments. We also discussed about characterization of different types of materials that we use in payments, soils, bituminous materials, aggregates and so on. In this lesson, we will be concentrating on analysis of flexible payments. The specific objectives of this lesson will be, after completing this lesson, it is expected that the student would be in a position to understand about different characteristics of payment materials to be considered for selecting an appropriate theory for analysis of flexible payments. As we know that we use different types of materials in payments, each material is different in terms of its behavior. So, we need to be able to model all these different materials independently and together as a payment structure, so that we can select an appropriate theoretical model for analyzing these payments, so that we can compute stresses, strains, deflections when these payments are subjected to loads and climatic conditions. It is also expected that the student would have learned the salient features of some popularly used theoretical models which are used for analysis of flexible payments. It is also expected that the student would have learned about different charts and tables that are available for solution of different types of payment systems, single layer system, multi-layer systems. Though there are nowadays softwares that are available for solution of any type of payment system, but for a student to be solving classroom problems and solving problems in examination, it is essential that we should learn what are the things that are available using which we can still solve payments, still we can analyze payments. So, that is what we are going to be concentrating on in this lesson. To begin with, as we discussed in the first lesson of this module, which was about general philosophy of payment design, payment performance can be explained in terms of the mechanistic behavior of its component materials. Payment is going to be comprising of different types of materials. So, how all these materials respond to the application of load, if you can understand that, we can explain the behavior of payments in a rational way, in a better way. The mechanistic parameters chosen to explain a particular type of structural failure, because the payments are going to be undergoing various types of structural failures or other types of failures. So, we would be selecting different types of parameters to explain different types of failures. These parameters would depend upon the type of payment, the composition of the payment, the materials that we use in constructing these payments, and loading and climatic conditions to which this particular payment has been subjected to. So, accordingly, we may have to be talking about different parameters for different types of payments, and we should be able to analyze and then find out the value of that particular parameter. Also, for computing these selected mechanistic parameters, it is essential to select appropriate material and geometric models. Like in the case of any other structure, it is necessary to select a proper geometric model and also a proper model which represents the material that are used in the payment. There are various models that are available to geometrically characterize any given structure, especially when we concentrate on payments. The common models that are used are beam, slab, a system of layers, or a system of finite elements. These configurations come with different foundation conditions. The foundations either being considered as elastic foundations or dense liquid foundations. For example, you see on the left hand side of this slide a multi-layered system, which is the most commonly adopted geometric modeling of a pavement, because we understand pavements are constructed in layers, it comprises of different layers. So, this is a very logical way of modeling pavements. But on the right hand side you see a finite element model in which the pavement is discretized into number of small elements. This would be required especially when the nonlinear behavior of different types of materials that we use in the pavement are to be properly modeled. When it comes to material modeling, materials are modeled on the basis of three main characteristics. These are the relationship between stress and strain. As you can see in this plot, if the stress versus strain relationship is linear, the relationship is called as a linear relationship, the material is called as a linear material. On the other hand, if the relationship is not represented by a straight line, then the material is nonlinear. The material is also described to be having stress dependent material properties. The second characteristic that we consider for selecting an appropriate material model is the response of the material on removal of a load, rather the recovery of the material on removal of load. As you can see from this diagram, for example, if the material is stressed, the corresponding strain is, let us say, epsilon. On removal, the material may instantaneously recover as shown by this, and it may recover completely, it is an elastic material. It may recover completely, but with time slowly. So, this is a material that is recovering fully because complete deformation is recovered. This is also an elastic material, but it has time dependent behavior, whereas this material has recovered partly and part of the deformation is not recovered, which is known as plastic deformation. The part of the deformation that is recovered is known as elastic deformation. So, this is partly elastic and partly plastic. So, we can see there are different types of materials: purely elastic, viscoelastic. This can be considered to be elastoplastic, partly plastic. So, depending upon the material that are used, different material will have different behavior, but hardly any of the pavement material can be considered to be having instantaneous recovery. Most of this material recovered to a great extent depending on the condition to which these are subjected to, but most of the recovery is over some time period. The next characteristic that we consider for selection of a material model is the time dependency. For example, if we stress a material to a constant stress magnitude sigma, and epsilon is the strain, the resultant strain. So, under this sustained stress sigma, with time, if there is no change in strain, this is a non-viscous material, but if strain changes for constant stress, these are viscous materials. Depending on the relationship between strain and time, if it is a linear relationship, so this is a linearly viscous material. If it is a non-linear relationship between strain and time, so that is a non-linearly viscous material. So, you have either a non-viscous material where the strain is not a function of time, or you have viscous material where the strain for a constant load, constant stress is a function of time. that variation can be linear, non-linear. So, various types of models, mechanical models are commonly used to describe the viscous behavior of materials. The two commonly used models are, these are the simplest models that are used to describe viscous behavior: Maxwell model and the Kelvin model. B and C, the second and third models are simple viscous models. There can be more complex models to properly model the complete viscous behavior of different types of materials. Normally, the instantaneous deformation is followed by time dependent and usually irrecoverable deformation. These are some simple mechanical elements that can be used to describe the mechanical behavior of different materials. For a simple pure elastic material, a spring can be used with an elastic component, a constant value of E. So, when this element is subjected to a stress sigma, the strain is simply given by sigma by E, this we all know. For a pure viscous material subjected to constant stress given by this. So, this can be represented by a dashpot. So, the strain is a function of time and given by the stress applied as a function of time, and this is eta, this is the viscous coefficient. Similarly, a slightly more complex behavior that can be given by Maxwell model, where the strain is represented by a combination of, this model is represented by a combination of spring and a dashpot. The strain as a function of T is given by stress divided by the elastic constant E plus stress and as a function of time and then viscous coefficient. This is a Kelvin model in which spring and the dashpot are put in parallel, and when this is subjected to sigma, the corresponding strain as a function of time is given by stress by elastic constant into 1 minus e to the power E into time divided by eta. The commonly used theoretical models for analysis of flexible pavements are: linear elastic theory is the most commonly used theory, and the geometric model that is used is layered theory. So, linear elastic layered theory is the most commonly used model for analysis of flexible pavements. Layered adoption of assumption we understand because pavement is a layered system, but we have to be justifying the assumption of linear behavior of pavements. This is due to the short loading time that we see in pavements, because the pavements are subjected to moving loads. They travel at different speeds, 40, 60, even 100 kilometers per hour. The loading time, the duration of the load pulses to which the pavement is subjected to will be normally be very small, 10 milliseconds, 15 milliseconds, 20 milliseconds. So, this is the order of the duration of the load pulses. So, for such small load pulses, the behavior of the pavement is generally observed to be elastic. Most of the deformation is normally recovered, although there is some irrecoverable component of deformation. So, that is the reason why most of the agencies use linear elastic layered theory for analysis of flexible pavement. Also, various field experiments conducted throughout the world, in various countries, have suggested that the stresses and strains and deflections observed in field can be adequately be explained by using linear elastic layered theory. So, that is the reason most agencies use linear elastic layered theory. There are of course other theories available in which different geometric and then metal models are used. To discuss the analysis of linear elastic multi-layered system, A simple system would comprise of a single layer characterized by elastic properties, elastic modulus value and Poisson ratio value, and in a single system the pavement would be subjected to normal surface load P distributed over circular contact area with a radius of A, and the corresponding contact pressure can be calculated from applied load and the contact area. So, if you consider an element at a depth z and at a radial distance r, there would be three normal stresses: sigma z, sigma radial along the radial direction and sigma tangential along the tangential direction, and also one shear stress. So, normally these are the stresses that we will have to be analyzing. For an axisymmetric case, as we just seen, there are three normal stresses: vertical, radial and tangential, and one shear stress on any cylindrical element in a homogeneous isotropic material. The simplest of pavement systems is a single layer pavement system. Let us consider the analysis of one layer pavement system. Although you normally do not find any single layer pavement system, because pavements are normally comprising of different layers. However, if we are trying to find out what are the stresses the subgrade is subjected to, it can be analyzed as a single layer system. Also, when you have very thin layer of pavement placed over subgrade, if we ignore the strength of the subgrade contribution of the rather the pavement, thin pavement, then the both the layers together can be approximated to be single layer, and that can be analyzed as a single layer. Also, many a time it becomes very convenient computationally to convert a given multilayer system into an equivalent single layer system and analyze it, because in some problems we have to solve the multilayer system repeatedly thousands of times. So, in such a case, if the multilayer system can be converted into a equivalent single layer system, lot of computational time can be saved. This is usually done. So, it will be very convenient to learn about analysis of single layer systems. Bosnesk, as you may be might have learnt in soil mechanics subjects, Bosnesk was the first to give a solution for a point load on an elastic half space. Elastic half space is a single layer system. Elastic half space the Bosnesk analysis considers a concentrated load P applied at the surface. So, for this system, vertical stress at any given location, that is at a given radial distance from the load and at a given depth from the pavement surface, can be given by this expression: vertical stress as a function of load applied and the depth at which the element is located, multiplied by a constant k, where k is a function of the location of the point in the pavement system. The Bosnesk analysis of solution of a single layer system subjected to a concentrated load can be expanded to a uniformly distributed circular load by integrating the point load over the entire area. The circular contact area can be distributed into small elements, and if the load that is coming on this small element can be considered to be P, concentrated load for which we have the solution. So, we can calculate the stress, vertical stress at a given location with reference to this load applied at this location. So, this can be integrated over the entire area giving us the vertical stress due to a circular contact area and uniformly distributed load. This obviously is a more realistic loading condition. Because of axis symmetry, as we mentioned earlier, in the case of an elastic Hall space, when it is subjected to uniformly distributed load, circular contact area, we have a axis symmetric case. So, we normally have 3 normal stresses and 1 shear stress to be analyzed. There are number of charts that are available. As I mentioned earlier, nowadays there are number of softwares available to easily analyze any payment system, but for those who want to do classroom problems and those who do not have access to any of these softwares, there are number of charts and tables available for different types of payment systems in standard textbooks. So, what I am going to discuss here over the next few slides will be some such systems that are available for solution of single layer system, 2 layer system and 3 layer system. So, in this slide we are going to talk about some charts and tables that are available for solution of single layer system. The first set of such charts were developed by Foster and Alvin. They have developed charts for vertical and horizontal stress and vertical elastic strains due to circular loaded plate and for a Poisson ratio value of 0.5. Subsequently, Alvin and Ullery developed more generalized solutions and presented them in the form of tables and charts. The input parameters that are to be considered for solving elastic Hall space will be load that is applied, the contact stress. Once we have these 2 parameters, we can of course calculate the radius of load contact area, assuming this to be circle, and location of the point at which we are trying to analyze stresses and strains, and of course the elastic properties of the layer, that is elastic modulus value and Poisson ratio value of the layer. Alvin and Ullery have given charts for 1 layer system for the following parameters. We can calculate vertical stress sigma z, we can calculate radial horizontal stress sigma r, tangential horizontal stress sigma t, vertical radial shear stress, vertical strain and other parameters. As you can see here, all these parameters sigma z, sigma t, sigma r are function of P that is applied and some coefficients A, B, C, F, D and so on, G. So, obviously, we have to find out for a given system what are the coefficients A, B, C, D and so on to be adopted. These values are a function of R and Z, which represent the location of the point in the payment system. Similarly, we can see expressions for other parameters like radial horizontal strain, tangential horizontal strain, vertical deflection, bulk stress, bulk strain, all in terms of the input parameters P, A, elastic modulus value E1, Poisson ratio value mu and the coefficients that are to be selected from the charts and tables that have been given by Alvin and Ullery, A, B, C, D, E, F, G, H. Typically, the charts look like this. For example, for identifying determining the value of function A, if you know the location of the point in the pavement, that is radial distance and depth from surface. So, this can be expressed in terms of radial offsets given by R by A, where A is the radius of load contact area and Z by A. So, the corresponding value of A can be selected from this table. So, we have similar tables available for all the other coefficients B to H. We will take up an example problem here. In this case, we have considered a circular load plate of 125 millimeter radius. The system, elastic system, has got a modulus value of 75 MPa and Poisson ratio value of 0.5, and we are considering a point which is at a radial distance of 125 millimeters and at a depth of 125 millimeter from the surface, and we assume that this to be circular contact area, and the contact pressure is assumed to be 0.4 MPa. So, for the given problem, R by A is 125 by 125, radius of load contact area is 125, location, radial location of the point at which we are trying to calculate stresses and strains and deflections is 125. So, R by A is 125 by 125, that is 1. The point is at a depth of 125, so Z by A is also 1. So, for values of R by A1 and Z by A1, these are the values of various coefficients that I have selected from the tables. So, for this sigma Z can be calculated as P applied pressure was 0.4 and coefficients of A and B. So, this is the vertical stress at that location. Similarly, I have selected all the other parameters C, F and other parameters, and the values that I have calculated for different other parameters sigma r, sigma t and so on are presented here for your reference. Okay, here we have vertical strain for the same problem and also the radial horizontal strain for the same problem. Once we are in a position to select all these parameters A to H, we will be in a position to simply substitute these factors into the equations and then calculate any parameter that we want to have. So, for a single layer system, we have charts and rather tables available using which we can calculate almost any parameter at any location in the pavement system. But as the number of layers increase, the number of variables that we have to handle and then how to present them, it becomes more complex. So, we will be in a position to calculate fewer and fewer parameters. When we move to 2 layer, 3 layer, 4 layer systems, we will be in a position to calculate fewer parameters. Let us consider a 1 layer system which has to be analyzed for multiple wheel loads. What we have seen so far is a pavement system subjected to a single load, but if you have a multiple wheel load, for example, there are 4 wheel loads here. So, how do you analyze for stresses and strains at any given point? In this case, we have 4 loads A, B, C, D. We are also considering, let us say, 2 points or rather 3 points, 1, 2 and 3. For example, if I want to analyze for point 1, what will be the stress and strain and deflection at that point due to all these 4 wheel loads? What has to be done is, we will simply do superposition, and whatever is the stress because of load A, load B, load C and load D at point 1, if you can analyze that, we will algebraically add all of them. So, for point 1, due to load A, the radial distance is 0. For load B, radial distance is x, and for load D, radial distance is y, as you can see from this figure. But for load C, the radial distance is given as x square plus y square under root. So, once we have the radial distance, and for all the 4 loads, we may be talking about a particular depth, it can be surface also. So, depth is constant, same for all the 4 wheel loads. So, we know the depth, we know the radial distances for all the 4 wheel loads. We simply find out the coefficients for all of them, calculate, possibly we are trying to calculate vertical stress. So, calculate vertical stress for all the 4 wheel loads A, B, C, D, add them algebraically. Similarly, if we want to find out stresses for vertical stress for point 2, for load A, R will be y, load C, R will be x, load D, R will be 0, load B, R will be x square plus y square under root. Similarly, for point 3, for all loads, R will be x square plus y square under root 1 by 2. So, what we are trying to do here is basically compute for individual wheel load and superpose. This we again have a similar example here, calculation of stresses due to multiple wheel loads. Here I have considered a dual wheel system. There are two wheel loads separated by a distance of 500 millimeters. Contact pressure is 0.4 MPa. So, we are trying to calculate stresses at a depth 125 millimeter. The distance between the two wheel loads is also given. Properties of the elastic layer is given. Modulus value of 70 MPa. Poisson ratio of 0.5 is there. We are trying to compute vertical stress at points 1, 2, 3. We are assuming that these loads have circular contact area. This is also very similar to what we have just discussed in the previous few slides. For point 1, due to load A, R by A is 0, Z by A is 125 by 125, that is equal to 1. These are the coefficients that I have selected from the tables for R by A equal to 0, Z by A equal to 1. So, sigma Z at 1 due to A is 0.258576 MPa. Similarly, for load B, R by A equal to 500 by 125. If we refer to the figure, we will know the radial distance is 500 divided by 125, that becomes 4. Z by A is again 125 by 125, that is 1. So, the coefficients for load B, A is 0.00761, B is minus 0.00608. For this, the vertical stress, of course, we can see this is very small, 6.12 into 10 to the power minus 4 MPa. So, if we are trying to find out total sigma Z at 1, this is a summation of the stresses due to the two wheel loads, that becomes 0.259188. Incidentally, the stress due to the second load because of its radial distance has been very insignificant. Similarly, we can calculate stresses for point 3 and point 2 in the same manner. When we consider single wheel layer systems, there are two different things that we have to consider. The loading can be considered to be either as a flexible plate or as a rigid plate, depending upon how the load is applied to the pavement surface. For example, if you consider load transmitted to the pavement through a pneumatic tire, it is not a very rigid plate, so it can be considered to be a flexible plate. On the other hand, if you have a very stiff plate over plate and then which are stiffened together, we have a system of very rigid stiff plate. So, we consider that to be rigid plate. Rigid plate basically does not deflect, and flexible plate also deflects. As you can see from this diagram, on the left hand side we have a system of flexible plate loading, on the right hand side we have rigid plate loading. So, on the left hand side this system gives you uniform pressure distribution, on the right hand side you have non-uniform pressure distribution. So, the analysis for these two systems will be slightly different. For example, if there is a flexible plate, the vertical deflection W is given as a function of the pressure that is applied, radius of load contact area, and of course, the modulus value of the pavement, radius of load contact area, and the depth at which we are trying to find out stress, Poisson ratio value. Okay. For a Poisson ratio value of 0.5, this simplifies to 1.5 Pa square into 1 by E A square plus Z square under root. For point on the surface deflection is given as 1.5 Pa by E. This is a very convenient expression for us to use. We will see how it can be used. So, the surface deflection for a flexible plate is given as 1.5 Pa by E, where E is the modulus value of the elastic house space, P is the contact pressure, A is the radius of load contact area. Similarly, for rigid plate, this is the expression for pressure. This is how the pressure is going to be distributed, how it is going to vary radially, given by this expression, but we normally use the average pressure. So, the vertical deflection along the axis of symmetry at the surface for a rigid plate is given as pi into 1 minus mu square Pa by 1 by 2 E, where E is the modulus value of the elastic house space. If we assume the Poisson ratio value to be 0.5, so the surface deflection simplifies to 1.178 Pa by E. Normally, we approximate this to 1.18 Pa by E. So, this is again another very convenient expression. We will see how we can make use of these two expressions, one for rigid plate, another one for flexible plate. Let us consider an example. Let us see, here we have a problem which has been subjected to a plate load test. The load applied is about 40 kilonewton and the radius of load contact area is 150 millimeter and the Poisson ratio value is assumed to be 0.5, as you can see from this diagram. So, we have conducted a plate load test on this single layer system. So, this being a plate load test, so this can be considered as a rigid plate. The average pressure that was observed, because we can observe the load that is applied and we can also observe, we also know the contact area. So, I calculated the average contact pressure as 0.566 MPa 40 kilonewton by the area of the plate. Say for this load, the observed deflection is about 2.5 millimeter at this location. This is surface deflection along the axis of symmetry of the load. Substituting this in the expression for surface deflection for rigid plate, 2.5 millimeter, this is the surface deflection that is measured, is given as 1.178. You can approximate this to 1.18 also, into P into A divided by E. E is what we do not know, but we have all the other inputs available. From this we can estimate what is the elastic modulus value of the layer. It works out to 40 MPa. So, this is a very convenient system, though not very rational, because this is a very static load, loading time is very large, but still we can get some idea about the elastic modulus value of a single layer system, provided we have a single layer system. We can conduct a plate load test on that, and using the expression for surface deflection, we can work out the modulus value of the elastic layer system. The next system would be an elastic multi-layered system. It comprises obviously of a number of layers, 1 to n layers. Each layer is characterized by the thicknesses and elastic modulus value and Poisson ratio value, and typically what we consider is a circular contact area load, uniformly distributed pressure applied at the surface. Let us see the assumption that we make in the case of a multi-layered system. In this, we assume that the material in each layer is homogeneous. We also assume that the material is isotropic. We assume that the metals are linearly elastic with an elastic modulus value of E and a Poisson ratio value mu. We assume that the layers are infinite in aerial extent. Horizontally, we assume them to be infinite in extent. We also assume each layer is of finite thickness except the last layer, bottommost layer, which is infinite in vertical direction also in one direction. We also assume the metal to be weightless. Other assumptions that we make about the loading conditions and boundary conditions are: uniform pressure is applied at surface over circular contact area, although we can still solve the pavements for other types of surface loading conditions. The continuity conditions are: between different layers, full friction is assumed between layers, that means same vertical stress, same shear stress, same vertical displacement and same radial displacement at the interface. We assume full friction and full contact also. We can also analyze the pavements for frictionless interface also, assuming that the interface between different layers is smooth, that leads to zero shear stress at each side of the interface. We normally do not consider shearing forces at surface, although some models are available which are capable of analyzing pavements for surface shear forces. The simplest of multi-layer systems is a two-layer system. Two-layer system could be simply be a granular layer placed over a subgrade, or a bituminous layer placed directly over subgrade, which is called as a full depth asphalt concrete pavement or bituminous concrete pavement, which is commonly used in United States, which is known as a full depth pavement. So, it can be either a granular pavement placed over subgrade or a full depth asphalt pavement placed over a subgrade. So, these two examples are shown in the slide. So, this is a full depth pavement, bituminous pavement, and this is a full depth granular pavement. For this also, Burmester has given solutions for solving two layer systems on the basis of linear elastic layer theory. Number of charts are available for solving two layer systems with both rough interfaces, and for normal uniformly distributed surface load, this is the most common assumption that we make about surface loading, and for circular contact area, typically charts are available for computing vertical stress and deflection. The vertical stress on top of subgrade, that is at the interface between the pavement layer and the subgrade, can be calculated with reference to this diagram. The points along the axis of symmetry of load can be considered. So, a two layer system is represented by two layers, the pavement and the subgrade, represented by thickness of the pavement. Bottom one has got infinite thickness, and modular values of the two layers and Poisson ratio value of the two layers, and the inputs in terms of loading are contact pressure and radius of load contact area, and this is a point at which we can analyze the pavement for vertical stress. This is a typical chart that is available for finding out vertical stress this is the vertical stress that we are trying to find out at a given depth, but given in terms of non-dimensional form, where P is the contact pressure that is applied at the surface, and similarly the depth at which we are trying to find out the vertical stress is also expressed in non-dimensional form, where the depth is divided by the radius of load contact area. This depth is nothing but the thickness of the pavement, because we are trying to find out interface vertical stress. You have number of charts available for different modular ratios E1 by E2, where E1 is the modulus value of the pavement, E2 is the modulus value of the subgrade. So, for different modular values you have modular ratio values, you have different charts available. So, for a given Z by A value and for a given E1 by E2 value, you can find out what is the corresponding sigma Z by P. Knowing P, we can calculate what is sigma Z value. From this chart, you could have observed that sigma Z decreases significantly as the stiffness of the pavement increases, that is E1 increases as the modular ratio value increases. Sigma Z at the interface is about 68% of P when we consider E1 by E2 to be equal to 1. E1 by E2 to be equal to 1 represents a single layer system, because both layers have got the same properties. So, it is a single layer system. So, when you have a single layer system at that particular depth, the stress is almost about 68% of what is applied at the surface. But on the other hand, when the modular ratio increases to about 100, that means the elastic modulus value of pavement is about 100 times the modulus value of subgrade, then this vertical stress at the same depth get reduced to about 8% of what we applied at the surface as contact pressure. So, modular ratio and thickness of pavement play a very significant role in reducing the stresses on the subgrade. A more generalized chart for determining the interface vertical stress is given in this chart, where A by H1, A is the radius of load contact area, H1 is the thickness of the pavement, that is the first layer. So, if you know the thickness of the pavement layer and also the ratio of E1 by E2 we can find out sigma z. Let us take up a problem for a two layer system. This is the design of pavement for the following criteria. The criteria is the interface vertical stress should not exceed 0.056 MPa. So, we have to select thickness H1 in such a way that what is the material to be used is also given. E1 has to be 250 MPa, this is the material we are going to use. E2 is also known, that is 50 MPa, and this is the vertical stress that at this location we are going to be concerned about, and radius of load contact area is given, contact pressure is given, all the inputs are available. We only have to find out what is the thickness that we have to place here. It is also given that Poisson ratio can be assumed to be 0.5 to simplify the calculations. So, the modular ratio E1 by E2 is 250 by 50, that is 5. So, for this sigma z by p is 0.056 by 0.56, the allowable stress is 0.056 and applied pressure is 0.56. So, the ratio of sigma z by p works out to be 0.1. From chart, entering with sigma z by p and for E1 by E2 ratio of 5, we can get the ratio of A by H1 which was on the x axis as 0.4, which would give us a thickness of 375 millimeter. If the same pavement were to be having E1 value of 5000 MPa instead of 250 MPa, E1 by E2 would be 100. So, for E1 by E2 of 100 and sigma z by p of 0.1 as you have seen here, A by H1 will be 1.1. So, the required thickness will be 135 millimeters. So, that would be the effect of using improved material, stronger materials. There are also charts available for determining the vertical surface deflection in a two layer pavement system. The expression is given here. This expression for surface deflection, if it is a flexible plate 1.5 Pa by E2 into F2. This is similar to the expression that we used in the case of a single layer system, but here we are using an F2 factor. For rigid plate 1.18, I have approximated this to 1.18 Pa by E2 into F2, this for a rigid plate. F2 is the deflection factor. Here we are assuming Poisson ratio to be 0.5 for both pavement layers. For homogeneous half space, H1 by A will be equal to 0, which gives us an F2 value of 1. We will see how we can make use of this system. This is the typical vertical surface deflection chart for a two layer pavement system. Here, if you know the thickness of the layer H1 expressed as H1 by A, if you know the modular ratio, then we can find out the deflection factor F2. Substituting this in the equation, we can calculate the surface deflection either for a rigid plate or for a flexible plate. Let us take up a problem and make use of this information of calculating surface vertical deflection. Here again we have a similar system, load plate 300 millimeter diameter, load applied is 20 kilonewton. This is a rigid plate, E2 is 50 MPa, thickness of the pavement is 200 millimeter. We are trying to find out value of E1. So, we have conducted a plate load test on this pavement. This is a rigid plate. So, for the applied plate load of 20 kilonewton, the surface deflection measured was, let us say, 0.25 millimeter. So, we are trying to estimate the elastic modulus value of the surface layer. So, for 20 kilonewton load and 150 millimeter load plate radius, contact pressure is 0.2829 MPa. So, measured surface deflection is 0.25, equating that to 1.18, this is a rigid plate, into P into 150 divided by P divided by 50, that is E2 into F2. So, this gives us an F2 value of 0.25. For an F2 value of 0.25 and H1 by A of 200 by 150, H1 is the thickness of the pavement layer, this is already given. The E1 by E2 works out to be about approximately 50 from the previous chart. So, E1 by E2 is equal to 50, therefore, E1 equal to 50 into E2, that is also 50. So, E1 works out to be 2500 MPa. So, in the case of two layer system also, if you conduct a plate load test and measure the surface deflection, and if you know the other properties such as the property of the subgrade, so we can easily find out what is the modulus value of the pavement material. Coming to three layer system, this being more complex, there are limited parameters that can be determined using various charts and tables that are available. Here the Poisson ratio value is assumed to be 0.5 for all the layers, and basically these are the parameters we can determine. Stresses at this location, this is at the interface in the first layer, stresses at the second interface in both layers. This system is characterized by thicknesses H1 and H2 and the elastic properties for all the three layers and the circular contact area applied at the surface. So, we consider non-dimensional pavement parameters to characterize this pavement, that is K1 expressed as E1 by E2, K2 expressed as E2 by E3, A load contact area divided by second layer thickness, H thickness of first layer and thickness divided by thickness of second layer. PT has given charts and Jones has given tables for calculating all these parameters. We can see the expressions. Sigma Z1 is given as a function of P multiplied by a parameter ZZ1. ZZ1 is what we have to find out from the charts. Similarly, sigma Z2 at the second interface vertical stress is given by ZZ2 into P. Similarly, sigma Z1 minus sigma R1 is given as a function of another parameter ZZ1 minus RR1 and so on. Basically, we have to find out these parameters for a given pavement configuration from the charts and tables. So, once we have all those parameters from charts and tables, we can calculate any parameter at these particular identified locations, because we are going to have all the three normal stresses sigma 1, sigma 2 and sigma 3, that is radial stress, tangential stress and vertical stress. So, we will be in a position to calculate the strains, as you can see from these expressions. There are various softwares available for analysis of multiple layer systems. Number of commercial softwares are available. These softwares can normally handle various layers, different number of layers can be handled. The loading also can be normal stresses, shear stresses at the surface can be considered. These softwares can normally handle rough and smooth interfaces, and there are finite element based softwares are also available, which are capable of handling nonlinear behavior of different pavement materials, especially the behavior of granular layers. To summarize, in this lesson we have learnt about various models available for modeling pavement systems. We also discussed about the considerations involved in the selection of an appropriate theoretical model for analysis of flexural pavements. We also discussed about various assumptions made in the popularly used Burmister's linear elastic layer theory. We also considered various charts and tables that are available for analysis of different types of pavement systems. Let us take a few questions from this lesson, which will be answered in the next lesson. What are the three main characteristics considered for selecting an appropriate model for materials? Explain how to estimate the elastic modulus value of a single layer system by conducting a plate load test on the pavement. What are the main assumptions associated with linear elastic layer system? And solve the problem given in the next slide. I am not going to read out the problem, this you can read. We will discuss this in detail when we discuss the solution of this problem in the next class. Let us take up the answers to the questions that we asked in the previous lesson, that was lesson 4.10. What does the compaction effort used in preparing Marshall specimens correspond to? Normally we prepare Marshall specimens subject to 75 blows on each face, especially for heavily trafficked volumes. The compaction effort corresponds to the density that is attained after several years of traffic. Why are the Marshall specimen tested at 60 degrees centigrade? It is typically assumed that 60 degrees corresponds to the maximum pavement temperature that pavements are normally subjected to, especially in the United States, because this is the specification that has evolved in the United States. Let us estimate the air void content in a specimen if its bulk specific gravity is 2.50 and the maximum specific gravity of loose mix is 2.60. We will quickly do this calculation. It is simply 2.6 minus 2.5 by 2.6 into 100. So, the value works out to be about 3.846%. Theoretical density minus bulk density divided by theoretical density expressed as percentage. Fourth question is, what are the advantages and limitations of using Marshall method for design of mixes? Marshall method of mix design is very simple, less costly, can be used by most of the agencies. That is the main advantage, and the specifications correlated to Marshall method have been correlated to lot of field performance, but on the other hand, the parameters that we measure, that is stability, flow, are not really correlated to actual field performance. That it does not explain fatigue performance of bituminous mixes, it does not explain the retting behavior of bituminous mixes, and these are not the parameters that are not fundamental in nature. We are not measuring the elastic modulus value, we are also not directly explaining fatigue and then retting behavior in terms of its fundamental properties. That is the main problem with Marshall method of mix design. Thank you.